there, and welcome to NASA Launchpad. I'm your host, Molly. We use electricity every day. It's in our homes, it's in our schools, it's even in our cars. So let's think of some ways of generating electrical power. Well, to start, there's solar power, which makes energy from sunlight. There's also wind power, which uses the force of wind to turn a turbine and make electricity. There's hydroelectric power, or water power, which uses the force of flowing water to do the same thing. And then there's something called radioisotope power. Not familiar with that last one? Don't feel bad, most people aren't, and it's because it's not something we use in our everyday lives. Radioisotope power systems are a special type of technology that NASA uses to provide energy to run some of its space missions that explore the solar system. Okay, so it's an electrical power system, you get that, and it's a type of nuclear power, but probably not what you're thinking. There's no nuclear fission, control rods, or cooling towers involved. So, how does it work?
A radioisotope is a variation on an atom. We have basic atoms like carbon, and it has an atomic number of 6. And that means there are 6 protons in the center of it. But it also has neutrons, and you can have a different number of neutrons. So carbon-12 has 6 protons and 6 neutrons, but carbon-13 has 6 and 7 neutrons. Plutonium-238, which is the isotope we're interested in, is an unstable atom.
If you have an atom that's not at a stable energy state, it wants to give off that energy and become a new element. And that's what happens with plutonium-238 in our case.
The whole process is actually pretty simple. As the radioisotope plutonium-238 decays, it produces heat, and that heat can be put to work to produce electricity. So a radioisotope power system is basically a device that uses heat to produce electricity, and NASA uses these for space missions. The great thing about radioisotope power systems is that they produce electrical power continuously in a predictable way for a long time. They produce this power whether it's sunny or dark, really hot or super cold, or whether the spacecraft's in a place that's dusty or filled with radiation from charged particles like the space around the planet Jupiter. So that means the use of radioisotope power enables long missions to some of the most extreme environments we can imagine. So, as we said, the heat from radioactive decay is converted into electricity. But how exactly does that work?
Thermocouples are very interesting because they're devices that you find all over your house, everything from your ovens to your hot water heaters. If you apply heat on one side of a thermoelectric and cold to the other side, you can get electricity out. And for space applications, mostly we use them to generate electricity to power our spacecraft. We have radioisotope heat sources that provide the hot side for our thermocouples, and then we have deep space providing the cold side.
Okay, check this out. Thermocouples take advantage of an electrical effect called the Seebeck Effect, and that occurs at junctions between different metals when they're exposed to a significant difference in temperature. For example, take one iron wire and one copper wire. Twist one end of the copper wire and one end of the iron wires together. Do the same with the other end of the copper wire and the other iron wire. Now, if you heat one of the twisted junctions and attach the wires to a voltmeter, you will be able to measure a voltage. That means electricity is flowing. And that's basically how the radioisotope power systems, the ones used by NASA so far, work. The heat from the decay of plutonium-238 is like the flame's energy given off by that match if it could burn steadily for years and years. Of course, it's not quite as simple as striking a match and heating some wires. Let's learn more about the engineering involved in this remarkable technology.
What's really exciting about RPS technology is that you're able to get so much energy out of such a small package.
Well, the first technology you need, of course, is to make the plutonium-238 and to refine it and get it into the form that you need. So there are a lot of nuclear technologies and a lot of chemical technologies that you needed to do that. And then there's all the materials technologies, the electrical technologies, and all of that has to go together in a way that is stable and that is compact.
We're literally flying spacecraft that have been up in space longer than 3 decades using these same radioisotope power systems, and they're still sending data back to us.
So, what's next for RPS?
ASRG, or Advanced Throwing Radioisotope Generator, is the next generation of radioisotope power systems that NASA is working on. The big difference between an ASRG and an RTG system is that it has moving parts, and in that generator there is a Stirling engine.
Well, the Stirling power system is actually 4 times more efficient than the materials type systems using thermoelectrics. It's a much more efficient system using a moving mass alternator than it is using the physics of the materials properties when you add heat on one end and have a cold side on the other. One of the things the ASRG allows us to do is first and foremost use a lot less of a precious resource, the plutonium-238. But secondly, it allows us to be more compact in the power system.
Okay, a quick review. Radioisotope power systems last for a long time, like decades. They're rugged, compact, highly reliable, and not easily affected by the environment where a mission has to operate. They're ideally suited for certain long-duration missions in the intense environments of space and on alien worlds in our own cosmic backyard. Well, that's it for this time. Thanks for watching. I'm Molly, and I'll catch you next time on NASA Launchpad.